Good afternoon. It's my pleasure to introduce Dr. Vareshwar Kurma. Dr. Kurma is a postdoctoral research associate in the Department of Computer Science at Purdue University. Vareshwar earned his bachelor degree in electrical engineering at Indian Institute of Technology, Delhi in 2009, and his PhD degree in computer engineering at Virginia Tech in 2016. He was the recipient of the Outstanding PhD Student Award by the Center for Embedded Systems for Critical Applications at Virginia Tech. He also had a short stint as a project assistant in the Department of Electrical Communication Engineering at the Indian Institute of Science in 2010. His research interests include discovering and mitigating security vulnerabilities in the communication protocols employed in cyber-physical systems, including smart home, smart transportation, and smart city. Vareshwar's research has featured in top-tier security venues, including ACM conferences on computer and communication security, CCS, and IEEE transactions on information forensics and security, TIFS. He also served on the TPC of flagship conferences, including IEEE conferences on communications and network security, CNS, and IEEE International Symposium on Dynamic Spectrum Access Network, DISPAN. So without further ado, let's welcome Dr. Kurma.
Yeah, thank you for the very nice and very long introduction. So I'm very glad to be here, and let's look into some of the security issues that we encounter in current vehicles and that we are going to encounter in next generation vehicles as well. So what is, let me first start with a question. So what is the first thing that comes to your mind when you think of an autonomous vehicle? So can somebody just tell me what is the first thing? And please feel free to stop me in between and then ask questions. Safety, okay, that's very nice. Yeah, that is very nice as well. Yeah. So yes, so those are the things that come to your mind when you first hear about an autonomous vehicle. So a few of the things that I would like to formally put, some of the advantages of these connected autonomous vehicles are driverless travel, traffic management, and minimizing accidents. So these are the numbers from India. So in top 4 cities in India, if you go outside with your car, you will spend around 45 minutes driving from your home to your office location. And also you will spend another 30 minutes in traffic jams. But the most important number here is the number of accidents and the number of deaths that happen. So in India, more than 100,000 deaths occur every year, which translates to 275 deaths per day. So it is very important that we develop a smart transportation system which takes care of the faults that drivers make on the road. Okay, so the idea of connected and autonomous vehicles has 2 components. So the first component is the autonomous component. So the autonomous component means that the onboard sensors on a vehicle, for instance the cameras, the LiDARs, they make decisions by sensing their environment. So the autonomous component is just an in-vehicular component where you have these nodes which are called electronic control units, which control each of the components of your vehicle. So one electronic component controls the brake, another electronic component controls your steering, and similarly there are around hundreds of electronic control units in your car these days. But all these electronic control units communicate over this network which is called controller area network, CAN. So by communicating over these, they make intelligent decisions. For instance, when you are actually using cruise control, your engine control unit, your steering, your brake, your accelerator, all of them are talking to each other and making intelligent decisions. So that is the part of the autonomous component of our architecture. Now let's move to the second component, which is the connected component. Now in order to enable a smart transportation, you need to make sure that the vehicles are talking to each other, and the vehicles are also talking to infrastructure, which may include traffic lights or other types of infrastructure. So when these vehicles talk to each other, they could make intelligent decisions in such a way. So for instance, when you are using just a camera, the camera will have to detect that the vehicle in front of you is slowing down, and then the camera could instruct the vehicle to enable braking, and then the vehicle which is behind the actually braking vehicle will be able to stop itself. But when you have this vehicle to vehicle communication, the first vehicle, even before it is going to brake, it can tell the vehicle which is behind it that it is going to brake, and then the second vehicle could also start braking. So it will be a very nice way to have this connected vehicle idea as well. So now the nodes in this connected vehicles idea are called onboard telematics units, OBUs. And the protocol that they utilize to communicate among themselves is called vehicle to everything V2X communication protocol. Okay, so when we look into the whole model of a connected autonomous vehicle, you can think of it as an OBU which has these two modems. One is called a V2X modem, which is required for connection over a wireless network, and the different vehicles talk to each other through this V2X modem. And then the OBU is also connected to the in-vehicular network through this CAN modem, which is the controller area network modem. And then this CAN bus is actually a wired protocol. These ECUs are following this wired protocol to communicate among themselves. And as I said, there could be a large number of ECUs which include body ECU, or which controls the doors and other stuff, and you could also have brake or engine. Now once we have this vehicle model, now what could go wrong here? So it is very nice to think about the security threats that we could have in any system, but it is particularly important to think about these kind of things for a very safety critical system like a vehicle. Now most of researchers here who are looking for look into these standard protocols, which could be a cellular protocol or which could be a Bluetooth protocol. And then we also have to look into this new generation V2X protocol, which will enable this vehicle to vehicle communication. Now when these vehicles were designed, they were never designed to be connected to the outside world through these communication protocols, because the controller area network, or the idea of having electronic control units to control each individual unit in a vehicle, it came around 1990s, when there was no concept that you should be able to use your mobile phone to open or to lock or unlock your door or to start your engine. These concepts were not there, and therefore in the design phase of these vehicles, the security was never considered. And then also there are these resource constraints which come because of these price issues. So because each vehicle contains hundreds of units, the price of it is very important for the vehicle manufacturers to keep the price of each unit very low, and therefore the units which are actually employed there have resource constraints in terms of energy and in terms of the bandwidth that they utilize to communicate with other ECUs. Okay, but now we know that it is possible to have bugs in these communication protocols, and once an attacker finds a bug in these communication protocols, it can find a foothold inside the vehicular network, and once it finds the foothold inside the vehicle network, it can take complete control of the vehicle, because as I said, there is no security that is built inside the vehicle. The messages that are being communicated, they are communicated in plain text, and therefore when the attacker takes just that foothold, it will be able to control your brakes, it will be able to control your steering wheel, and it can do many other things, very interesting things to your vehicle. Now, it is not that there is only one particular manufacturer which could be affected by these bugs. So, researchers have found a large variety of bugs in all different top manufacturers of vehicles, which include Tesla as well. And so, in order to just illustrate what can happen when somebody gets into your vehicle, I would like to show this quick video in which the attackers are able to do very interesting things. So, here you see the attacker controlling the steering wheel of a vehicle, the door lock and unlock feature, the RPM meters, the brakes. Yeah, so it can actually do many interesting things. And what the way they did it was that they found a bug in the entertainment system that was installed on the vehicle. That entertainment system utilized a cellular connection, and therefore the attackers were able to get into the vehicle wirelessly. So, they exploited the bug in the entertainment system to ensure that they have full control of the vehicle. Now, because of this vulnerability in which was shown in 2015, Jeep had to recall 1.4 million cars and do this security patch for their entertainment system, so that this security vulnerability could be mitigated. Now, some of the researchers in IBM, they actually went ahead and analyzed what could be an impact of these kind of security bugs. So, they found that if these type of bugs were not mitigated during the design phase, and the manufacturer would have to recall all these vehicles and then mitigate them, it costs the vehicle manufacturer 1000x more to do that. And therefore, it is very important that we develop these security mechanisms which prevent all these different types of attacks during the design phase of the vehicle. Okay, so now let me go into the technical detail of my talk. So, I will go into we just looked into the two components of this connected and autonomous vehicle idea. So, I will go into these two different aspects and talk about the different attacks and possible defenses in those components. So, looking into the first component, which is the autonomous component, we will look into an impersonation attack. And in this impersonation attack, we assume that the attacker has already gotten foothold into the vehicular network, which means that perhaps the OBU is already compromised. And now we will see what this OBU, the compromised OBU, can actually achieve. Okay. So, as we already said that this in-vehicular network does not employ any kind of security, which means that it does not employ any encryption or authentication mechanism. Now, so what would be the solution? So, the researchers have proposed that how about we install an intrusion detection system on the bus, which detects these different types of anomalies which can occur because an attacker has started launching some attack on the vehicle. So, the IDS will try to detect these anomalies and raise an alarm. Okay. But yeah, so you might realize that these IDSs are never perfect. So, you always have this cat and mouse game. So, the first attacks that were proposed were message impersonation attacks on the CAN bus, and then people came up with these anomalies that can occur in messages and detect those anomalies to come up with an alarm system. Then this race continued, and currently we are at this stage where the state of the art intrusion detection system utilizes this voltage based fingerprinting technique. Now, let us see what are these voltage fingerprinting based intrusion detection system. So, if you see an ECU, the architecture of an ECU, you will see that when the ECU wants to send something on the bus, there is a very simple mechanism to do it. So, when the ECU wants to send a bit 1 on the bus, it sends a volt 0 on the bus, and when it wants to send a bit 0 on the bus, it will send a value of voltage to be 2 volts. Now, since this mechanism is implemented in hardware, and hardware is actually a set of transistors and resistors. These things are never perfect. So, in inducing such voltages are never perfect. So, on the bus you will see these different fluctuations in the real value of the voltages. So, what the researchers did was they actually found that these voltages have a distribution, and if we extract significant number of features from these distributions, it is possible to differentiate between the senders. So, if an engine control unit is sending a message, it will have a particular distribution of voltage values. If the brake control unit is sending a message, it will have a different distribution, and therefore, the proposed mechanism was to train a machine learning algorithm with these features, and then at the in the operation phase, when somebody sends a message, you match the fingerprint of that message to the learned fingerprint, and if they do not match, you raise an alarm. But there is an issue here. So, these voltage fingerprint based IDS, they require regular training, because the voltage fingerprint can change with temperature, because when you have these resistors and these transistors working, they actually change their behavior at different temperatures, and then that behavior also changes over time. So, when they get old, their behavior changes. Therefore, this regular retraining is required in these bits. Okay, so, now let us see how these bits, these defense were evaluated in the prior art. So, in the prior art, what they were doing when they were proposing these defense mechanisms, that they considered a victim. So, let us say the engine control unit is a victim here, and then they said that okay, we will have a WIDS defense there, and then they considered one attacker. So, in this case, let us say the telematics control unit is an attacker, and now what the attacker could do was, the attacker could only heat itself or cool itself to change its voltage characteristics, because the voltage characteristics are generated by the hardware of the vehicle. So, even if you have compromised an attacker, you cannot compromise its hardware, and therefore, the voltage fingerprint cannot be changed, but the attacker could just only try to heat or cool itself to change the voltage behavior. But you see that the defense is actually using a machine learning algorithm, and there is an asymmetry here. So, the defense is using the machine learning algorithm, but the attacker is very naive here. So, therefore, we saw an opportunity to ensure that we can come up with a better attack that has been proposed in the prior literature. So, therefore, we came up with this attack, which we call DUET. So, this attack requires two compromised ECUs. So, we have hundreds of ECUs in a vehicle. So, we considered that let us have two compromised ECUs. So, one could be the telematics control unit, which has this cellular connection to the outside world, and the other could be the VCIM, the vehicle communication interface module, through which you use your mobile and you connect using the Bluetooth. So, the Bluetooth is actually controlled by this VCIM. So, let us have these two compromised ECUs in our attack model, and then these two compromised ECUs, they would employ an adversarial machine learning technique to actually counter the machine learning based intrusion detection system. So, the specific the adversarial machine learning technique that we utilized is called training set poisoning, and let us see how that works. So, this is again revisiting the same concept, that different ECUs will have different voltage characteristics, and they will have different voltage distributions. So, here I have enumerated them, the three ECUs, as victim, attacker and accomplice. So, now in this case, if the attacker wants to impersonate the victim, because their distributions are different, the WIDS will detect that impersonation attempt. But now what we will do is, we will try to bypass the WIDS. But here one important thing to note here is that these all three of them have this unimodel Gaussian distribution, which means that they have some variance around just one mean. The voltage values have some variance around that one mean. Okay. So, what we will do in the training phase of the WIDS is that now the attacker will start transmitting simultaneously with the victim, and it will corrupt some of the voltage samples that are being transmitted by the victim. So, when it actually corrupts some of the samples that are being transmitted by the victim, it will lead to a bimodal distribution, which means that now there are two means. One is corresponding to the benign samples, and the other one is the superimposed samples, which are called corrupted samples here. So, since the superimposed samples will have a higher voltage values because of the superposition, you will see a bimodal distribution when you see the voltage characteristics of the victim. Now, in the training phase, the WIDS is now learning from this bimodal distribution. Okay, so what is the next step then? So, now in the test phase, which is the operation phase of the WIDS, what we will do is, now the accomplice and the attacker, they start transmitting together. So, the message that is being forged, it now contains the fingerprint or the voltage samples corresponding to this attacker plus accomplice. Now, again you see that because there are two ECUs transmitting together and they are superimposing their voltage samples, you will again see a bimodal distribution, which means that so in the training phase we have tricked the WIDS to consider any bimodal distribution as the victim, and therefore, in the test phase, if the WIDS sees a bimodal distribution, it will classify it as coming from the victim, and therefore, the accomplice plus attacker is classified as coming from the victim, and therefore, we have successfully bypassed the WIDS detection mechanism. Now, you will notice that in order to do this simultaneous transmission, there are some challenges. So, the first challenge is to do time synchronization, which means that the attacker should be able to transmit at the same time as the victim. And in order to do that, what we do is we track the victim's periodic transmission. So, the victim, all the ECUs on the CAN bus, including the victim, they transmit messages periodically on the bus, and therefore, if we could carefully track these messages, we will be able to ensure that the attacker could transmit simultaneously with the victim. And then the second challenge was to superimpose some of the voltage samples, and for that you need to guess what would be the payload in the victim's message. So, here that we call as payload synchronization. So, we notice that on the CAN bus, the messages on the CAN bus, they have some counters, they have some multi-valued numbers which could be easily guessed, and they also have some sensor data which do not change for a very long time. So, for instance, many of the things, so the status of the gear, the status of the door, they do not change for a very long time unless the user or the driver makes some action on those things. So, therefore, we found that it is able to predict the payload of the next message by seeing the current message of the victim, and therefore, we were able to do this payload synchronization as well. So, in order to do this payload synchronization, we came up with this idea of predicting these payloads, and we found that we could do this prediction with very high accuracy. So, in this curve, what I am showing is that, so let me just get into the specific example. So, this curve shows the cumulative number of messages in which you could predict certain number of bytes of from the victim's message. So, here you could, on the y axis we have the number of messages, and on the x axis you have the number of bytes. So, you could see that when the total, so the byte 0 means the total number of messages that an ECU transmits. So, on the for the red curve you see that out of 50 messages which you could see on a particular vehicle, there were 45 messages where we could easily predict at least first 2 bytes of the data, and therefore, an attacker could easily transmit simultaneously with those first 2 bytes and corrupt the voltage samples of the victim. Okay. Okay, so now this is the final result that we have. So we actually conducted our attack duet on a test bed consisting of these electronic units which were emulated using Arduino boards, and then we also conducted attacks on 2 real vehicles. One was Impala and the other one was Cruise, and we achieved a very high success rate, which is on the y axis on this curve, and on the x axis we have the length of the predictable payload prefix. So which means that if we were able to corrupt more samples in the victim's message, we were able to achieve higher attack success rate. So if we were not able to corrupt anything in the victim's message, the attack success was very, very low. So at max we were able to achieve a more than 80% success rate even in vehicles, and an 80% success rate is good enough for a masquerade attack on a cyber physical system. Okay, so now I would like to present an attack demo which we created by attacking a real vehicle. So in this attack, our goal is to impersonate the RPM meter while evading the widths. So the first what we did was we did some reverse engineering to find out what messages correspond to the engine RPM. So here you see that the engine RPM is 700 revolutions per minute. Now these widths algorithms, they were implemented in our laptop, and we collected the voltage samples through the oscilloscope that you see here. So in the first stage, which is the training stage, you see that nothing is changing. We are corrupting the voltage values of the victim, but the width is learning from those corrupted values, and nothing is, you do not see any change here. But now when the next attack phase starts, you see that the RPM raises to 7000 revolutions per minute. You could never reach that value in these cars. If you are driving a Formula 1 car, possibly you might reach that number, but in a real car you will never reach that. So what we are doing is we are impersonating the engine and sending these fake messages, forged messages to the this RPM meter, and the RPM meter is accepting those values. And then we notice that the widths does not raise any alarm, because we were able to do this successfully able to do this adversarial machine learning approach of training set poisoning. Okay, so that is the end of this first part. I would be happy to take some questions here. Yes.
For remote attack surface, I saw that for the wireless attack, it involved targeting the like the single chip modem,
Yes.
like the Roadlink modems.
Yes.
Would there be a way to try to mitigate wireless attack surface by making that protocol authenticated to try to reduce that?
Yeah, so definitely if you enable authentication, you should be able to do you should be able to reduce the attack surfaces. But the argument here is that you will always have some bugs in Bluetooth, you will always have some bugs in cellular protocol. We always see researchers coming up with these bugs, and once you have these bugs, no matter what type of authentication you have in these vehicles, an attacker could always find a way to get into the vehicle. Yeah.
I have a question about the something your testing framework. So what I want to ask is that so basically as far as So in the vehicle, so typically, especially your target vehicle, how many issues there are?
So in a Tesla, you might see around 200 electronic
200?
control units. Yes. So each component of your vehicle is these days now being controlled by one electronic control unit.
Okay.
But in an old vehicle, you would see a dozen electronic control units. So the vehicle on which we are working, it has around a dozen electronic control units, the 2011 Impala.
Then probably I guess that some of the at least some of the ECU component may have some controller logic like a PID controller or whatever. How many control logics are there probably?
So these are not very complex electronic units. So they have usually one MCU, and then that MCU has the architecture of that MCU is very, very simple. So probably I would say so they have so one MCU can have multiple chips, and one of those chips could be a CAN controller, which enables that MCU to communicate with this with other MCUs through this CAN bus. So yeah, so I guess that is the overall architecture of an electronic control unit that you see in a vehicle.
Then just my question is how many PID controllers are there probably out of all the CAN nodes something like that?
So I would not be able to tell you the exact number, but there should not be many PID controllers in a vehicle.
Okay.
Yeah. Yes.
Okay, so I have a question. So once we find there is a vulnerability in an ECU, so what's the possible options to fix this, or they are totally cannot be fixed?
No, you can always do a firmware update. So that is what Jeep did. It recalled the vehicles and did a firmware update to fix those.
So that means we need to use some devices to connect the car and do the update.
Yes.
Okay.
So for these vehicles, so now people are coming up with this idea of over-the-air update. So they could actually update the firmware of an ECU over the air. So they do not need to actually recall all the vehicles and then fix the vulnerability.
Okay, I see.
Yeah.
Thanks.
Okay. Okay, so now that you know that authentication is very important before getting access to a vehicle. Now let's see an adversary model in which the attacker is actually trying to get into the vehicle. So the victim is now the onboard unit, and the attacker is trying to get into this onboard unit. So as we just discussed earlier, what we need is an authentication protocol here, which prevents this adversary to get into the vehicle. Okay. So now let's first talk about the need for these connected vehicles. So I would like to highlight the need for these connected vehicles through this video, which does not have so we don't have a way to hear this, but yeah, let me just stop it. So
do you have a earphone out jack on your laptop?
yes.
I thought it was the guy in the video was saying that.
We can do.
No, it's fine. I could just tell them it is fine. It is all right.
Okay.
Yeah.
Okay. Just
Yeah.
because we can plug that thing into do
No, that is fine. This Tesla vehicle, it actually rammed into a police car which was stopped in the middle of a road. So what happened was the Tesla vehicle did not, going at 60 miles per hour, did not expect any vehicle to be stopped in the middle of a road. And when it actually noticed a vehicle, although it tried to brake, but it could not brake, and it went directly into that vehicle and causing an accident. So now what was wrong in this scenario? The issue was that these sensors that you have on a vehicle, they have limitations. So for instance, the camera could only see for a particular distance, and in fog probably the camera will not be able to see anything. So these onboard sensors have limitations, and therefore we need the concept of these connected vehicles, so that these vehicles could talk to each other over a wireless medium and tell the status, tell their status to other vehicles. So for instance, in this case, the police car would have broadcasted its information that it is stopped in the middle of a road, and if this Tesla vehicle would have received that information 1 kilometer when it was 1 kilometer away from the vehicle, it would have made a better choice. So now in order to enable this idea of connected vehicles, the Society of Automotive Engineers, SAE, it has defined a set of basic safety messages. Now these basic safety messages include broadcasting information about location, speed, acceleration. In some cases you also the vehicle will be needed to broadcast this forward collision warning, intersection movement assist. So now these particularly these location, speed and acceleration messages, they are transmitted periodically over the air. So one of the standard value of that period is 100 millisecond. Okay. So now let's see what properties we need for this connected vehicles idea to be secure. So the first security property is that we need to validate those safety messages. So if a vehicle is receiving those safety messages about the location, about the speed of another vehicle, it should be able to authenticate those messages, and therefore authenticity is a criteria here. Now we also need to provide privacy to the senders. So these senders are actually broadcasting their private information about their location over the air. So it is very important for any mechanism to ensure that this private information about the location cannot be exploited by an adversary to track the movement of the driver. Also the information about speed and acceleration, they could be utilized to profile or fingerprint a driver. So the driver it is very important that we provide this privacy to the driver, and therefore the security property that we want here is privacy. And then in a vehicular environment we also need this property of revocability, because you may have many vehicles, malfunctioning vehicles, and you will need them to not come on the road, and therefore you want to suspend the license of those vehicles, and therefore you need this third property of revocability. But all these three components can be provided by this mechanism called privacy preserving or anonymous authentication, and one nice way to do it is called group signatures. So here I would give you a very high level overview of group signatures, which was proposed by the researcher at Stanford named Dr. Dan Boneh. So he is a cryptographer who has developed many different types of signature schemes. Among them is the group signature scheme, which actually provides privacy preserving authentication. So in this environment there are three entities. The first is called the group manager, and as the name suggests, it is responsible for generating the group public key. Now what is the need for generating this group public key? So as the name suggests, the group signatures, the anonymity here is in terms of the group, which means that every sender will broadcast information saying that I am part of a particular group, and the receivers will verify that whether this signer is part of a particular group or not. But the signers will never embed their own information or their own identity in the signatures. So therefore the larger the group, the signer's privacy will be higher. So the verifier will not be able to know who is transmitting, it will only be able to know that someone from the group is transmitting the message. Okay, so the group manager's task is to set up the group by generating the group public key, and then it will also assign secret keys to these signers. Then it is also responsible for publishing a revocation list, which will contain the information about those whose licenses has been suspended. Now the signer's task is very simple. It has to just generate an anonymous signature of the over the message that it wants to broadcast. And then the verifiers has to do two things. First is to ensure that the signature is authentic. So the message that it is receiving is authentic, is determined based on the authenticity of the signature, and therefore the verifier has to verify that. And then the second task that the verifier has to do is to check the revocation status of the signer, which means that the signer is not revoked. Okay, now let's look at the scale of the network that we are actually considering here. So we and the functions that we are employing in these group signatures. So in this group signature scheme, one fundamental function was called a bilinear map operation, and we ran that operation on an Intel i7 processor based computer, and found that it took 2 milliseconds to run that bilinear operation, bilinear map operation. This implies that the verifier could only run 500 operations per second. Now the dilemma of the verifier is that the verifier does not know the identity of the signer, and the revocation list does not contain the identity of the signers. It actually contains the secret keys that were allotted to those signers, and therefore when the verifier receives a message, it has to look to each entry in the revocation list, see if that secret key which is in the revocation list has been utilized to generate that signature or not, and then move to the next entry in the revocation list, which means that the computation cost of the verifier is actually linear in terms of the size of the revocation list. Okay, so now you could see that a verifier could only run these 500 operations. So potentially the verifier could only check a revocation list of 500 entries. Now let's see the scale of this network. So now we consider a simple scenario where you have a road with 3 lanes and two-way highway, and you consider one vehicle in each 50 meters. So the distance between two vehicles is 50 meters in each lane, and we consider this typical communication range of 1 kilometer, and we again consider the typical periodicity of 100 milliseconds for the location and the other information that each signer is broadcasting. So this translates into 2400 vehicle to everything communication messages per second, so V2X messages per second. Okay, and now let's see the number of revoked vehicles. So in US there are around 11 million revoked licenses currently. Now if we reduce that number to a vehicle, so the vehicles will be malfunctioning, but that malfunctioning could come from the malfunctioning of the components of the vehicle, or that malfunctioning could also come from the malfunctioning of the drivers, and therefore we should consider a conservative number. So the conservative number that I consider here is 1000 revoked signers. Now this means that you need to run that operation of bilinear map 2400 into 1000 times. Now you cannot bridge this gap between the capability and the requirement by using simple techniques which you could employ to do parallelization or hardware acceleration, and therefore it is imperative that we develop a novel mechanism to address this challenge. Okay, so what we proposed was that rather than verifying the revocation status of a vehicle deterministically, how about we verify the revocation status probabilistically. So now you could think of the analogy with the Miller-Rabin primality testing algorithm, where the primality of a very large number, if you want to determine it deterministically, it is very computationally expensive. But if you want to just use the probabilistic algorithm proposed by Miller and Rabin, it is very efficient. Although that efficient algorithm will not give you 100% accurate result, but still almost all systems in the current world, they utilize this probabilistic algorithm called the Miller-Rabin primality testing algorithm. Okay, so our idea was to have this group signatures with probabilistic revocation. So the first contribution was that we come up with this idea of alias tokens, which these signers could embed in their signatures. So these signers cannot reveal their identity in the signatures, but what we wanted to ensure that these signers reveal something in their signature, and that we call alias token. So now these alias tokens are given to these signers by the group manager, and these signers now reveal this alias token, one alias token in each signature. Okay. Now the second contribution is the signal processing part, where we check this, we utilize this alias token that has been embedded as part of the signature and come up with a probabilistic revocation check mechanism. So now when the group manager revokes a signer, it actually revokes these alias tokens, and now the verifier actually checks the revocation status of these alias tokens in order to check the revocation status of the signer. Okay, now let us go into the details of these contributions. So for this embedded alias token, so what we did was we utilized the same fundamental operation, which was called the bilinear map operation. I will not go into the details of the function, but you could see that it is a very simple operation. So that bilinear map operation E, when conducted on two parameters u raised to the power a and v raised to the power b, it is equal to the operation when it is implied on those two parameters u v raised to the power a b. So this bilinear map operation is the fundamental operation which provides privacy to these signature algorithms. Okay, so what these three entities in our signature scheme do? So the first step is to generate the group secret key, which is the same here. Now the second step is to generate these alias tokens. So the group manager generates these alias tokens and assigns them to the signers. But the most important thing to do here is to generate the signer's secret key. And now you see that here in this third step of the group manager, the signer's secret key is generated using all the alias tokens that has been assigned to the signer. So the signer's secret key is now related to all of these alias token. Now what the signer does is signer generates these other parameters, some parameter b and some parameter c, but the important point to note here is that the parameter b is generated by all the alias tokens that it has, and the parameter c is generated by all alias tokens except the alias token which it wants to reveal in its signature. Now when it generates a signature, it sends the information or the zero, so what we call is zero knowledge proof of knowledge of these three parameters a, b, c, and it reveals this alias token xi as well. And this verifier now checks whether the signer has a valid secret key. So it runs the same bilinear operation which is called E, and it checks if the parameters a and b satisfy a particular equality or not. And then again this alias token is now the verifier ensures that this alias token is actually cryptographically linked to the signature or not. So it again uses the same bilinear map operation to check for this linkage of the alias token with the signature scheme. Okay. Now the second aspect, how we utilize these alias tokens to actually do the revocation check mechanism. So for this we utilized a very popular technique which is utilized in 3G communication. So it was in 3G communication, what happened was that the users were allowed to transmit at the same time and at the same frequency. But when all these different senders transmit at the same time at the same frequency, it is difficult for the receivers to decode those signals. So this concept of spreading codes was developed, where these codes are utilized by different codes are utilized by different senders, and they code their signal using these different spreading codes. And when a particular receiver is interested in a particular transmitter, it will use the same spreading code, and then it will be able to extract that message from the overlapped signal, and it will be able to know what the sender was transmitting over there, although the sender is actually sharing the same spectrum and the same time with other senders as well. So if you use the same spreading code, if the sender uses the same spreading code and the receiver uses the same spreading code, they could have this communication of information. Okay, but if they use different spreading codes, they will not be able to know what they have, what the sender has sent, and they will also not be able to know anything about that information. So that there is a privacy component there as well. Okay, so what we did here. So what we did was, we actually took these alias tokens and mapped it to spreading codes, and then when the group manager has to revoke these different signers by revoking their alias tokens, we revoked these spreading codes corresponding to those alias tokens. And the way we revoked this is to generate a revocation code. So rather than generating a revocation list, now we generate a revocation code, which is actually a sum of all these revocation codes. So now you see that the analogy of sharing the same time and the same frequency using the spreading code comes here, that now you have, what you have done is you have generated one code, which is called revocation code here, by summing up all these spreading codes which were revoked. And now when this when a verifier has to actually check the revocation status of the signer by looking at an alias token, so that what the verifier can do is, the verifier could map that alias token to a spreading code, which we call here as alias code, and then it could compute a correlation with the revocation code, and this correlation value will lie between 0 and 1. So the basic thing here is that if the correlation is above a threshold, which means that the alias code was encoded in the revocation code, which implies that the signer was revoked, and if the value is lower than that threshold, implies that the signer was not revoked. So this is this mechanism ensures that you are actually using a probabilistic mechanism to decide on the revocation status of a signer. Okay, so using this probabilistic mechanism, we were able to significantly reduce the computational cost of the group signature mechanism. So here you see the blue curve, which is the curve for our group signatures with probabilistic revocation, and the red and the green curves are from the prior art, and we see that we were able to significantly reduce this computational cost and make our scheme implementable in a standard vehicle to infrastructure communication network. So you, on the x axis we have the number of revoked private keys, and you see that even if the number of revoked private keys reaches some number like 10,000, on the y axis we have the computational overhead in milliseconds. So you are still less than 100 millisecond. So the verifier would take even less than 100 millisecond to verify each of those messages, and I will remind you that 100 millisecond is the time when you receive a message. So it is very important that you should be able to verify a message within 100 millisecond. Okay, so I would just conclude here. I already talked about the two components of this connected autonomous vehicle. In the first part I talked about this attack Duet, which evaded the state-of-the-art fingerprinting technique that is employed by the intrusion detection system. And the second part, I utilized this idea of probabilistic revocation to come up with this scalable privacy-preserving authentication mechanism for the V2X communication. So the goal here is to actually come up with an end-to-end authentication mechanism, and even my current research directions are to enable this smart and secure transmission by transportation by enabling this end-to-end authentication. That is the end of my talk, and I will be happy to take more questions. Yes.
I'm wondering how the threshold is.
Go and use your microphone.
Yeah. So
How
Yes.
the threshold is determined in the verification?
yeah. So we ran some simulations of how many number of revoked signers if you have, and you generate a revocation code, and you do the same mechanism of setting up the threshold and detecting the revocation status of the vehicle. So we found that in order to achieve, these are all mechanisms to ensure that you achieve a particular false alarm rate and a particular detection rate in that system. So we found that if you determine a particular false alarm rate, you could find the threshold, and then you could set that threshold in your scheme. So you will have. So we first start with the particular false alarm rate, and from there we determine the threshold value.
I see. Thank you.
Yes.
Yeah, you mentioned that the autonomous vehicle update their firmware by using the over-the-air channel.
Yes.
So I'm curious about whether when they conduct over-the-air firmware update, they utilize any authentication or firmware signing method or not. Yeah.
So I think they do utilize it. So at least I know that Tesla utilizes this over-the-air update mechanisms, and they do utilize authentication while doing that.
Any other questions? No? Okay, I'll speak.
Yeah, thank you.